So, good afternoon, everybody. Welcome to the joint ESRF ILL colloquium. It's a real pleasure to be back in the auditorium for a scientific event, because this has not happened since more than 1.5 years. And so we're testing new technology, which hopefully will work as expected, but well, we're the first to try this at ESRF. And so it's my pleasure to introduce today's speaker, who is Paul Loubert from CEA Arpajon. Paul is a well-known expert of ultra-high pressures, to which he dedicated his entire career, and more specifically to the use of synchrotron radiation for the study of matter under extremely high pressures. Paul studied at École Normale Supérieure in Paris, and then at Université Pierre et Marie Curie, from which he received his PhD. And in 82, 83, he did a postdoc at Urbana-Champaign, University of Illinois. Then he joined the CNRS as a research scientist from 83 to 98. And in 98, he was appointed as the head of the high pressure group of the CEA in Arpajon. Paul is well known at ESRF because he's a very frequent user of our beamlines, and also because since about 5 years, he's a member of the Science Advisory Committee of ESRF. And he has received a number of scientific awards, in particular the CNRS Bronze Medal in 88, the ESRF Young Scientist Award in 96. So that's a good sign of his fidelity to ESRF. He received the Bridgman Award in 2015, and last year, 2020, the Grand Prix Émilie du Châtelet from the French Physical Society. So the research of investigation of matter under very high pressure is, of course, of great interest, because that enables us to understand what's going on in the interior of planets. But there are also some very fundamental physics problems that are of great interest in the field. And one, maybe the most important problem people are interested in, is what happens to hydrogen, the most elementary, the simplest element under extremely high pressure, because 80 years or so ago, it was predicted by Wigner and Huntington that this would become a metal. And this has become a holy grail of ultra-high pressure science. And Paul has devoted a considerable effort on this topic. And a little less than 2 years ago, he had a great breakthrough. And that's what we are going to hear about. Before starting the talk, I give information for the people who are following us on Zoom. So welcome to you as well, all colleagues from everywhere. And you are, of course, very welcome to ask questions to Paul as well by using the question and answer box in your Zoom window. And for the lucky few who are in the auditorium, we will ask you to use the microphones that are on the side, because so that the sound retransmission to Zoom is done optimally. So I think that's all I needed to say for the introduction. And Paul, we're looking forward for your presentation. Many thanks.
Okay, so I think I'm going to be here for just speaking a start. Then I would move over there, and probably those on internet will not see my face. So it's a real pleasure to be here. Thank you for the invitation. It's a real pleasure to be able to give a talk, presential, after some 2 years of lack of that. The aim of my talk, I twofold today. One is to show you that synchrotrons radiation is important to achieve detailed measurement under extreme conditions. And that would be illustrated on synchrotron measurement, which is infrared measurements in front of a solar synchrotron. But I will mention some X-ray diffraction measurement that can be made or have been made. And the second aim of my talk is to show you that a simple problem such as the metallization transition of hydrogen has attracted so many studies, and to show you why so many people have devoted so much effort in this problem. So this work I'm going to present was with Paul Dumas and Florent Shelley. So Florent Shelley is working with me at CEA, and Paul Dumas was a beamline scientist at Soleil on the Smith beamline when he started this experiment more than 10 years ago. He's retired now, but he has joined our group at CEA as a scientific expert. So we cannot speak of hydrogen without mentioning Neil Ashcroft, who unfortunately passed away this year, a few months ago. So Neil Ashcroft is a famous high pressure, is a famous condensed matter physicist who devoted many of his work to the problem of hydrogen. And he has made many publications that has been very, very inspiring for us experimentalists. The first one was that he predicted at the end of the 60s that hydrogen would be high temperature superconductor at the time where it was believed that no superconductivity, conventional superconductivity would go higher than 30 K. And recently, since it was so difficult to obtain this phase of hydrogen, he said that probably the same physics could be discovered in hydrogen-rich system. And at the time, he was speaking of CH4 and so on. But then with Roloff Mann at Cornell, they really showed that there was a new chemistry of hydrogen with metal, and they predicted these superhydrides. I will speak of that later. So indeed, since hydrogen is a fundamental problem, and it started, hydrogen has been the fundamental system for the start of quantum mechanics, from the hydrogen atom, hydrogen molecule, and then when you go on a collection of hydrogen molecules, proton of electrons, what are the stable phases? So it's clear that the stable phases at ambient pressure at low temperature, you condense, you make it liquid, and then a solid. And the solid can be quantum in the sense of the rotational properties. The spin of the nuclei are important. But then in the 30s, Wigner and Huntington applied the first approach of this Fermi gas to calculate the stability of solid, and they predicted that under very high pressure, this molecular solid should become a metal with proton and an electron. It's because when you confine this hydrogen molecule, the kinetic energy of the electrons is so high that the electron wants to delocalize. That's a simple idea. But the calculations how the properties of this metal has been fascinating the theoreticians for more than 80 years now. At the time, it was predicted that hydrogen would be a metal around 25 GPa. So it's 250,000 times the atmospheric pressure. Then at the end of the 80s, in the 80s, few theorists applying the method of band structure calculation showed that probably hydrogen could become a metal without destroying the molecule, keeping the paired the pair of the molecule and becoming a paired metal. You have to realize that all those predictions are difficult because proton and electrons must be treated as quantum particles. The double wavelength of the proton is 3.1 angstrom at 30 K, and at 200 K is even nearly 1 angstrom, which is more than the interparticle distance at this extreme pressure. The Bird-Oppenheimer parameter is not small, so you cannot probably can have an effect. And also the 0-point effect are very important. So this is why it's a fascinating problem. It's an 80 years old question. Metal hydrogen should show have been predicted to show many quantum many-body properties, like room temperature superconductivity. I spoke of that with Ashcroft. It could be a super solid metal deuterium, superunique phase. It could even be a liquid. If you compress it at very low temperature under extreme pressure, it will become a liquid, and this liquid will be a superfluid superconductor phase, a quantum many-body state that has not been observed in all the other systems. But the difficulty of describing hydrogen, because it's so quantum, is a very difficult many-body descriptions. You've taken to a strong electronic correlation, zero point effect, anharmonic effect, the question of Bohr-Oppenheimer approximation that I spoke of. So it's really a test bed for ab initio calculations. And that demands reliable experimental data, and I insist on that, because the theoreticians are making a lot of effort to try to compare to experiment, and you have to be clear that we are making this reliable experimental data. Metal hydrogen also is important for astrophysical objects, not in a solid phase, but in astrophysical objects such as the interior of Jupiter or Saturn or other exoplanets. It's what we call in the form of warm dense states. So it's dense, a little warm, so in a fluid phase, but the density is important. And I will show you that the density can also bring conducting to metallic phase, insulating to conducting phase, which is called metallic in this warm dense fluid. So the density is important, and some of the properties are similar to what we observe in condensed matter physics. Metal hydrogen also have given remarkable intuition for materials. I was speaking of the superhydride, and here is an example of LH10, which is really a dense network of atomic hydrogen with some Lantern atom in it. And the last thing for experimentalists is it's really the most difficult system to study under pressure, because it's very compressible, it's very reactive, and really studying hydrogen has pushed the developments of novel high pressure approach, and I will show you that. So if we could recover metal hydrogen at ambient pressure, it could be a breakthrough material. The storage of hydrogen would be 100%, would be ideal hydride. It would store a chemical energy which would be much greater than the H2O2, which is a factor of 10 order greater. Would be a room temperature superconductivity. It will show strong photonic superdiffusion. Its density will be 6 times that of cryo-deuterium. And probably you've heard this summer they achieved this fusion by laser, initial confinement fusion at Livermore in the States. And if we could have a target with this metal hydrogen, it would also change the easiness of this process. So the essential question is that can we recover it at ambient pressure someday? So it's, as I said, it's more than 40 years of claims and experimental approach. In dynamic measurements, you want to, in dynamic measurements, it started in the 70s, really in the 70s, there was some static and dynamic approach to try to observe it. In a dynamic approach, since you launch a shock or a dynamic compression, you heat at the same time. So the way you heat, the sample change the temperature. And if you heat very slowly, you can have isoentropic compression, so you don't heat too much. And for some experiments, in all these dynamic experiments, they observed a change of conductivity, either by reflectivity or by measuring conductivity. The issues are that the pressure temperature locus is not very precisely known, but roughly the various measurements has been going up to 10,000 K to a few thousand K. And you see, as you increase pressure, it's at lower temperature. So it's becoming a density effect, and it's becoming like a transition induced by density, like metallization. In static measurements, there's been a claim in the 70s, in the Soviet Union, big press was constructed. The claim was that hydrogen was a metal at 100 million atmosphere, but it was not reproduced, and it was suspicious. And recently, there were claimed that atomic metal hydrogen was observed really at 500 GPa, and we will come to that later. So these measurements has been questioned and not reproducible. In contrast, in dynamic measurements, it's less question, it's more the question, where are the measurements being done? So I would like to present our measurements while using the synchrotrons, how we did it and why we believe it's more reliable and that we did indeed some measurements. So I'm going to present to you the experiment we performed more than a year ago. Okay. More than a year ago, and another experiment we performed at the beginning of this year on D2, and that show that reproducibility and that we could do detailed measurements, and it really address the isotopic difference between these two samples. So we performed the measurements at the synchrotron Soleil, which is in Orsay, France, on the infrared beamline, and roughly this is the kind of sample we observe over there. So before we start, where was expected the transition pressure to solid metal hydrogen? So based on calculation, most of the calculation was really converging that this transition should take place between 350 GPa and 550 GPa, which is 3.5 million atmosphere to 5 million atmosphere. And experimentally, some years ago, we measured the direct gap of hydrogen and extend what other people have been doing, and extrapolating this evolution, we also expected the closure of the band gap, which is the transition to the metallic phase, around 4.6 million atmosphere. Then there is another question: how hydrogen will become a metal? Will we go directly to an atomic metal or to a paired metal, as I described to you? And the most advanced calculation predicted that indeed there should be a paired metal in between. Should go from insulating in this monoclinic C2 over C phase, and then there should be a molecular metal, and then go to the atomic metal. So what needs to be done to do a convincing evidence for the insulator metal phase transition? First, we have to demonstrate that we can do measurements in the 400, 500 GPa pressure range, 4 to 5 million atmosphere pressure range. That is above what has been really done by the static pressure community. And we have to do that on other systems before claiming that on hydrogen. We have to have a signature of the insulator metal phase transition. And we have to measure the evolution of the properties of hydrogen until it reaches metallization, so that we can understand what the physics is at stake and do comparison with calculation. So for those who are not familiar, we are using the diamond anvil cell, which is a tool of the high pressure static community, which is compressing the matter between two diamond anvils. And the matter is inserted in a small sample chamber, which is a small hole drilled into a metal sheet. This is a standard tool, very used. And there are two items I would like to mention that have been important for our measurements. First, we're using a membrane to drive the force on the piston to drive smoothly the pressure, which provides a great control of pressure. And as you will see, we are doing the measurements in front of the infrared beam. If we are losing by slightly misaligning the sample, we will never get it back. And then we use synthetic diamond, high pressure diamond, because first they are transparent for the infrared, and also they are defectless, so it's well better. Then the other important question is, how do we measure the pressure? And in this pressure range, there is no calibration. We are not in front of a synchrotron where you can use a metal to measure the pressure. The luminescence gauge like Ruby, which is the standard measurements of pressure in this 1 million atmosphere range, is not valid anymore. So there has been a scale that has been proposed by measuring the Raman phonon of the diamond at the interface with the sample. And so diamond has a strong phonon mode at 1333 wave numbers and just of numbers. And then if you do the Raman measurements through the diamonds, you see that you really crossing all the pressure range until you reach the highest pressure at the tip. And so if you do, and so you have this kind of spectra where you have flat and then the small steps and then the distribution of pressure in the sample. And really you have to measure this edge, the frequency of this edge. And two scales has been proposed, calibrated, one to 300 GPa, another was calibrated to 400 GPa, but there was some other estimation, we believe, in it because they use a wrong equation of state for the platinum they were using. So we are using scale 1, and this is part of the discrepancies in the literature on these hydrogen claims, that some people are using scale 1, some people are using scale 2. So we have to be careful in what scale we are using. And we are using scale 1 that we believe up to this pressure are more robust than the other one. Probably the reality should be a little in between, but more precisely to scale 1. So you can make a really 100 GPa difference in this pressure range. Then we have to overcome, so as I showed you, the diamond NV-cell is a standard tool. And usually people are using a diamond that have a bevel shape, so flat diamond, flat tip, and then bevel that are polished by like diamonds by polishing the diamond. But despite many efforts and many groups, they are faced that, in fact, reliably you cannot go above 4 megabar with the right scale. And so to go above this pressure, two devices was proposed lately. One by the Dubrovsky group with putting two type of putting a little ball of diamond on top of the diamond tip, and we designed a new kind of tip, which we call toroidal, that we could make by using a FIB machining of the diamond. And with that, we could show that the sample was not changing to what we were having in standard diamond cell. And we could reach, on gold, on argon, we could reach at least 600 GPa. And this is a kind of, I like to say that the profile of these new envelopes were made by measurements at the SRF, where we had beam times to really scan the profile, do the measurements with metals, and really optimize this diamond tip. And if this is a kind of diamond tip, it's really like having, again, you have the tip and then really having this little other envelopes on top of it, but it's part of a single crystal, so you can do exactly the same kind of measurements as in standard, with the same dimension of sample as in standard diamond cell. And I would like to show also that this type of diamond tip is deforming very well under pressure, and I will show you that you can recover your envelopes even going to very high pressure. Then which injector you have to use for metal hydrogen? So previous claims for laboratory measurements, some have used reflexivity, like in the work of Ag Silva and Diaz. No measurements, just showing a photograph. And there is a problem here. I will discuss that at 500 GPa, the diamond should be black. And there is a problem. And there is no measurements also on the way going up to this pressure, what has been the evolution of the properties of hydrogen, so we can follow and be sure what has been measured. There's been other claims by doing, putting electro-resistivity measurements to some leads in sample. There is always could be some problem of hydrogen is very active, forming hydrides, or it can be, the sample is very small, can be touching them. So there could be some problems. So we decided to do a non-intrusive measurements, an optical measurements, and doing infrared spectroscopy you can address, as we show you, the electronic properties of the sample, the chemical change of chemical, if there is no change much of chemical, unless the chemical bond of the molecule. And you can also follow the structural change indirectly by following the signature with the excitation mode. So high pressure bench was built on the Smith beamline, and the sample was in a cryostat at low temperature, and we have also Raman measurements that we can shift. We have two non-reflective reflective objectives of large frontal distance, and the beam, the infrared beam, is 25 micron, very bright, as on the cyclotrons. And if you go inside the diamond, it's even reduced by the index of diamond in this cell. The important point is that you can make a very nice infrared signal. You can have a very nice infrared signal, even with a 5 micron diameter sample. You have to know that we are probing the range roughly 8,000 wave numbers to 1,000 wave numbers. It is 10 micron. So 10 micron means that you are the limit, more than limit of diffraction of your small sample, but you still can make a lot of nice measurements. So the reference bench, the important part, as I said, was that you have a high stability. And so you cannot change, you have to change the pressure remotely with the membrane. If not, you will lose your alignment. So now the infrared absorption measurements. First, to convince you that infrared measurements are a signature of the change of electronic state from going to conducting to metallic phase. This is a measurements that's been done on oxygen. On oxygen is a molecular solid that metallizes also around 100 GPa, which is more easy. Has been characterized by optical measurements, by electrical measurements, even measuring the superconductivity. At the SRF some years ago, we measured the structural change at the insulator connecting insulator metal transition. Here is a single crystal of oxygen, which is like a metal inside helium. And when you do the measurements with infrared in the same pressure range, in the same exactly as we did for hydrogen, you see that you have a decrease of the intensity on the high wave numbers, and you have to, and then on the low wave numbers, you have a decrease. You have a decrease of the intensity, which is because there is an indirect gap closing, and then the direct gap is closing. I will come to that later. So we're confident that these infrared measurements are a signature of metallization. So now on infrared on the solid hydrogen, so above 400 GPa. First, with the membrane, we can follow very well the pressure increase. So we have a nice curve, and we measure the steps of the Raman, as I showed. We are using the scale 1. And then the infrared spectra are very, the raw spectra are very good quality, even at some pressure. And you can see that you have here the decrease of the intensity is related to the closure of the decrease of the direct band gap. And then this is a Vibron here, which is very strong in phase of high pressure phase of hydrogen. So we have the essential information on the spectra. Then we have to analyze. So like I said, the band gap this is the sign of the closure of the band gap. And okay. And at some stage we had complete absorption. So if we analyze that with absorbance, then we can point where the band gap is. The band gap, which is the distance between the valence band and the condition band. So the energy you have to give to the system so that the electron becomes conductor. And though the band gap is decreasing, this was the visible measurement we did some years ago. And at some stage, you have a decrease, and so the band gap is going to be very small. There was some discussion on our data saying you cannot say that the band gap has closed because you cannot go below 0.1 EV. Probably we cannot remove this possibility of a very small direct band gap, but we have a transition. And what's very important here is that we have the change of the small wavelengths, small wave numbers, evolution of intensity is rapid, and we have no sign of an indirect gap coming in. So that the semi-metal is taking over. We have a change in the direct gap only. And the measurement is reproducible. If you decrease the pressure, you recover the same measurement. We have a vibron, so we can measure the vibron and the phonon. We have two modes, vibron and phonon, which is a signature, has been calculated as a signature of the phase, which is a monoclinic phase. Relay is like hexagonal plane with a molecular line in the plane. This has been predicted by ab initio calculations. And relay, we are observing this kind of infrared signature of this phase. So we believe this phase is stable until the metallization. And we believe since we have a reversible transition, we have formation of a molecular metal. And this is a sample before the transition. You can see it's black, and this is rhenium gasket. So gasket should be the metal, but since the diamonds are under extreme pressure at 1412 VPa, the diamonds start to look a bit red. And after the transition, is still black. And there has been some calculation that if you have an atomic metal hydrogen, it should be highly reflective. If you have a molecular metal hydrogen, it should be less reflective, 0.4. So it's compatible with this calculation. But now, so we have to prove that we can do this measurement is really reproducible, and they are detailed and quantitative. So we redo this year the same measurements on deuterium. But then we have to go. You have to go to higher pressure because you have anisotropic ISO. I will show to you on the gap. Again, we have nice infrared spectra. Do the same measurements, nice measurements of the pressure. We do the same analysis with the gap, and then we see that the gap, there is a strong isotopic shift on the gap. Deuterium is metallizing above hydrogen. You have to go to higher pressure to observe that, which is a true quantum effect. We also observe the same stabilities, not due to structure, the same signature of the vibron and phonon. And so it's the same structure. So H2 and D2 are compressed in the same structure. And what's interesting is that if you normalize the vibron measurements of hydrogen to the one by the square root of the mass compared to deuterium, it seems that hydrogen is lower, so there is a softening more of the hydrogen molecule than deuterium molecule, which could explain why we go in the direction that you have a metallization before for hydrogen than deuterium. For the phonon, the romanization, they are almost agree, so there is no, this is working very well, as expected. And then, since we published our measurements on hydrogen, there has been many ab initio calculations trying to calculate the gap of this phase, C2 over C phase. And you have to go calculating the gap, you have to go to more advanced calculations. And there's been one doing quantum Monte Carlo calculations where you treat at the same level protons and electrons. And their gap is matching quite well with our evolution of the gap. Then there has been another calculation doing this path integral molecular dynamic simulations, and again it's this one, the stars, so they are matching well. I should say that if you do the best calculation by DFT, without going with this, taking into account this coupling between the nuclear effect, the quantum effect, and the electrons to calculate the gap, you have a gap which is much higher. And another one which was calculated differently is this quantum effect on the gap. And in fact, for all these calculations, it's the corrections they have to do of the quantum calculations, taking into account this quantum effect on the proton to reduce the gap. And the quantum Monte Carlo, which is the most advanced, is -2 eV reduction. And the other are -1, -3 eV. And our measurements for H2D2, since we are making with the same pressure, same measurements, the shift is quite accurate, we believe. And assuming the isotopic shift in 1/square root of m, we have a reduction to this effect with 1.5. So quite good, reasonable agreement with this most advanced calculation. So if we summarize the isotopic effect there are on this on hydrogen metallization, there is a small effect on density. In fact, hydrogen at a given pressure, hydrogen higher 0 point motion should have a slightly higher volume, which doesn't go in the direction of lower metallization. You have a softening of the bond, as I said, as you see on normalization of the vibron. But more puzzlingly, you see that the gap is this transition of the gap is occurring for the same value of the bond gap, which goes in the direction that it's really the effect of the band gap that is driving the configuration of the band gap that is driving this transition. And this has been proposed by Dogan and Marvin Cohen this year, that the observed metallization of hydrogen can be interpreted as a band structure effect. So it's really a change with the same structure, a change of the configuration of the bands compared to the Fermi level that opened a new direct gap. So it could go in this direction. Very interesting. Then to progress, we need some structural X-ray data to be able to validate if you have the C2/M. This structure is this C2/C structure. There has been here we have since, as I said, I am a user back to 30 years ago. And in fact, doing the X-ray diffraction of hydrogen was our first measurement when I came here, tried to do with this new facility. And recently, there's been a measurement of the equation of the structure of hydrogen up to 240 GPa at the APS by a Mao group. Here we have progressed over the years to try to measure accurately the equation of state, and we achieved 200 GPa, but we couldn't solve the structure of phase 3. But still, our measurements are a strong test of the ab initio calculation. So we need really this third generation synchrotrons, the X-ray diffraction were limited to below 250 GPa. With extreme beamline ESRF, extremely bright ESRF, we have the possibility to extend this X-ray diffraction up to the metal transition, and this is one of our plans. And especially since you see the sample at the 300 GPa, 400 GPa, the sample is quite big. It's over 5 to 6 micron diameter, and this is quite a big sample. Now, what's next? Observing the observation of meta-hydrogen is a stepping stone to our disclosing novel quantum many-body effects. So the quality of the samples that we have obtained is encouraging to do measurements, more measurements. And we believe that this should be done with optical properties. It's much more easy. So the transition to metal atomic hydrogen should be done by reflectivity jump. As I said, molecular atomic hydrogen is as reflectivity of 0.4, and the atomic metal should be very bright, like aluminum should be 0.9. And then reflectivity can also give you an idea of the superconductivity. And if you do the reflectivity in the infrared, you can measure the superconductivity gap, but not going so far in the far infrared, you can have an anomaly on the reflectivity around 3 to 1 micron. And then this anomaly reflectivity could probably be taken, if measured, as an indication of superconductivity. Then you can do also NV magnetometry to disclose the Meissner effect of the superconductivity. And these are measurements that we are pushing and developing. This is not synchrotron measurements, but lab measurements. And the way we want to do is to do imaging in visible infrared, do reflectivity. This is quite, to do accurate measurement is quite complex, even if you want to, especially if you want to do reflectivity measurements with a sensitivity better than 1 or 2%, which is needed to disclose this subtle change of reflectivity. and if you have a spatial resolution of more than 3 micron. And with this infrared in the 2.1 micron range, which is here, which should be needed for the measurements of the superconductivity, we have a spatial resolution that can allow to see the very small sample of hydrogen, not at very high pressure, but still. And these measurements of reflectivity are accurate. We can even see a change of reflectivity at the phase transition on tin. Then NV magnetometry is another example, which is we are collaborating with Jean-François Roch, which is pushing for that. So NV is a defect in the diamond. It's a 2-level system, and the photoluminescence is dependent on the state of the spin of this level. And you also can, so since this one is more brighter, you can polarize under illumination one of the level 0. And so then, since you have polarized your system, with photoluminescence, if you send a microwave and you scan the microwave, you can really probe where there is a transition resonance and probe this level. And since this level is of the spin 1, is sensitive to the Zeeman effect, and so it can be split under a magnetic field, and you can detect the magnetic field on change of magnetic field over your sample. So it's a way. So it's a very simple optical measurement of magnetism, which is spatial resolution, and this has been applied to 2 measurements to standard superconductor like MGB2 at 7 GPa, and the work is ongoing at 15 GPa on cuPRAT. But to go to higher pressures, there are much more properties to disclose and effect to master, and there's a lot of work being done by the Jean-François Roch group to push that in extreme conditions. But it's very promising. So as I said in the beginning, metal hydrogen can be useful for understanding planetary interior. Indeed, planetary miscibility of hydrogen, the miscibility of the hydrogen and helium inside the Jupiter is related to the properties of hydrogen and when the fluid molecular is becoming a metal. And we showed recently using big laser that there is a phase separation under the condition inside Jupiter. What's important here is that there have been some calculation that there is an isotopic shift, should be an isotopic shift between H2 and D2, even in this region of metallization of hydrogen inside the planet. And the calculation, the isotopic shift is of 30 GPa, which is of the same amount of what we're measuring at very low temperature. So it's just an example to show you that what we are measuring on the sample to disclose quantum effect can be important to explain more the properties inside that planet. Now we have the question of the recovery of H metal, and the transition to a pair metal is reversible, completely reversible. We recover the hydrogen gas. There has been a long debate since the 70s that probably metal hydrogen, the atomic form of metal hydrogen could be reversible, could be metastable. The most recent calculations say that you can recover it probably to 250 GPa, but at the lower pressure it could be unstable. That to be seen. But what I want to show you is that, as I said to you, that the toroidal envelope we are using show excellent deformations. And this is a diamond envelope that has been recovered from the experimental on hydrogen for 4 million atmosphere. You see the center is completely intact. There's no deformation of the diamond. And the one recovered to above 5 million, roughly 5 million atmosphere is also recovered intact. So there is a way to recover, if it's metastable, to recover it at ambient pressure. But there has been, as I said at the beginning with Nelashkov, they were pushing for other systems where we can probably approach the properties of hydrogen, metal hydrogen. And this is with superhydride. So there's been this prediction of many systems where you mix metal and hydrogen and you form this compound very rich in hydrogen. And there's been a big big effect because the superconductivity was measured by the Hermes group and the MD group really roughly at almost room temperature with an isotopic effect. The structure of these hydrides has been characterized using synchrotron X-ray diffraction. And I would like to say that the iron hydride was the first superhydride that was characterized, and it was done here by Charles Pepin in 2015. And then these hydrides are really can be considered as additive volume of metallic hydrogen and metal. So there is a lot of interest in these new systems. But there have been some claims that even a room temperature superconductivity has been reached by gas and all in the ternary compounds, carbon, sulfur, and hydrogen. But this is much questioned now. And really, to progress, the synchrotron is important to characterize the structure, and we have to answer the question: which extent they are proxy of hydrogen metal? What are the superconductivity? Will they be metastable at ambient pressure? There's much work to be done, and probably the tools that are developing for doing for characterizing hydrogen at high pressure will be helpful for that, especially for detecting the Meissner effect, which is still not convincingly measured in those superhydrides. So in conclusion, I would like, I hope I showed you that as John Balmer said more than 20 years ago, no, more than 50 years ago, that hydrogen appears to be predestined more than any other materials to open new avenue to research into the nature of matter and its properties. And this really, hydrogen has been inspiring the modern physics and has been the essential element of physics. And indeed, hydrogen is the essential element to reveal the properties of matter elements. Thank you for your attention.
Thank you very much, Paul, for the fascinating presentation on this extremely exciting and hot debated topic. So we're going to take questions now. For the people who are following the colloquium on Zoom, please use the question and answer box to ask your question. We shall nevertheless start with questions from the auditorium. So we would like to, Matteo, please go to the microphone and press the button, please.
Yes. So you mentioned about the transition to the metal phase of hydrogen, that there have been some remarks on the fact that you haven't been able to reach a measurement of the clock. You have been able to measure a gap down to 0.1 eV. But my question is, I mean, I see clearly that there is, you measure a very sharp transition. It's fully reversible. So clearly there is a transition phase. And I was wondering if one wants to place, let's say, the devil's advocate, if there is any hypothesis about a possible alternative state that is not exactly metallic phase, and if there is any theoretical studies that have predicted such kind of alternative state.
So so there is this possibility that it's a very, the dye gap is very small. There is a claim that, in fact, before it's a semi-metal with an indirect gap. So my point is that if it's a semi-metal with an indirect gap, then the number of carrier is very small because we don't see any absorption in the small wave numbers, whereas we see those absorptions for oxygen and probably will for others when you have even when they are not before the transition to metallic state. So in our case, we don't have evidence of the semi-metallic phase. And then we have evidence that there is complete absorption infrared, and probably it could be a 0.1 EV gap, but then going a little higher, it would go to phase transition. Now, your question, the work of Marvin Cohen of this topological change of structural change, not the topological in the sense that the Fermi energy is going to open a small direct gap, has been predicted. And then when you increase pressure, so it's a little metal in this case, with a direct gap, little metal, and then the density of carrier is going to increase with pressure. So the way to resolve that is really to do this reflectivity measurement, or to increase higher pressure and to go to the atomic metallic phase. The other comment is that for the other claims of semi-metal, if they are very small number of carriers.
Any other question from the auditorium? Yes, go to the microphone, press the button.
Yes, I have a question. How do you know that this metallic properties or this image you see is not coming from diamond itself? That the carbon atoms experiencing this high pressure, they are not metallizing, for instance? How do you know that?
Because the measurements when you go down are exactly reproducible. We show that exactly the same spectra, the same. So there is no change of the diamond. And then we say, okay, it's the properties of the diamond, but doing deuterium at much higher pressure, we show that we measure hydrogen before, and so it's not coming from the diamond. So there are two facts: the fact that it's completely reversible and the diamond doesn't change at all. We recover perfect single crystal diamond, not attacked, and the measurements are reversible going down. And then the fact that we measure deuterium at much higher pressure and hydrogen shift means that what we're measuring on hydrogen is really due to hydrogen.
All right, thanks. And the second question actually got inspired from the article in Nature 2 months ago about metallization of water. They claim they metallized water used at vacuum conditions on the droplet of sodium-potassium alloy. And instead of using pressure, they use this one. Do you consider that maybe not only the pressure is the only factor which might help you to get metallic hydrogen? Do you want to combine it maybe?
This is what they are doing with superhydrides. They were putting an element in water to dope with electrons. So it's not a metallization of pure water. They put this sodium in it to give electrons to the metallic state. The same thing with the superhydrides. You make a metal that can give also electrons. You have your hydrogen network, and the properties of the hydrogen networks dope with the electron of the metals. The slight mass of hydrogen makes the ITC properties, but the metal is contributing to the network of hydrogen. This is same thing.
But they are using like large metals, like lanthanum was there, right?
Yeah, sulfur. Yeah.
But the more electron donating properties are the metals with fewer electrons, right? Like lithium, sodium, potassium. Why are they not using them for superhydrides then?
Yeah, but the pressure changes things, changes the chemistry, and you have to give a little, just a little electron.
All right, thank you.
Thank you. Yes, please.
I have hello, thank you for the nice talk. I have a similar question actually about the, you mentioned that the next step is to measure the reflectivity, and I also wanted to ask, how do you think that the optical changes in the diamond anvils are going to affect, okay, I see the problem, how the optical properties of the diamond, which is changing from red into black, are going to affect such kind of measurements, which is such a, I would say, continuation to the previous question. Thank you.
That's a good question. That's why in this pressure range, very high pressure, the gap of the diamond is closing in the visible. Okay, it's decreasing in the visible. So it's why it's happening red and black. But in the infrared, it's still very, very transparent. So it's why it's very important to do the reflectivity measurement in the infrared. We will be able to observe this high change of reflectivity by doing the measurements in infrared. It's why we make this effort to do the measurements at 2.2 micron or even less. And then there are some difficulties, but it's a way to go. Showing a reflectivity usually will be impossible to do in the visible for this reason. At 5 million atmosphere, the diamond will be completely invisible. But it's not close in infrared.
Thank you, Paul. We can come back to questions from the auditorium later, but I'd like to also get colleagues on Zoom to ask questions as well. And we have a question from John Eggert. You showed that the diamond absorbs strongly in the visible above 450 GPa. Have you measured diamond in absorption in the infrared at these pressures?
Yeah, good question. This is ongoing. We have an experiment that will be going. If you want to probe to really close the gap, you have to go to above 500 GPa, and this is what we are planning to do. Yeah. Not yet, but it has to be done.
Thank you. A question from Kamil Dziubek. I understood you perform your infrared experiments for hydrogen and deuterium metallization at the same temperature. Is there any experimental evidence that the phase boundaries on the transitions between phase 3 and metal for both hydrogen and deuterium are almost vertical with T, as you have shown on the phase diagram?
In fact, I didn't show that they were vertical. They are slightly increasing with temperature, but we have preliminary measurements. I'm not going to comment on that.
A question from Vasily Minkov. Can you comment on metallization through the closing of indirect gap, which we repeatedly done with electric measurements to the archive, and I guess it's the group from IRMETS.
Okay, this is so first to compare, we have to compare the same. This is going to be a bit technical. We have to compare the same pressure scale. So this is the publications. The publications. Those publications where they are mirroring the semi-metallic behavior, they use scale 2. So when they claim 440 GPa, it's in fact less than 400 GPa, it's 390 GPa. And what I showed is that for oxygen, when we see in the far infrared, when we see the absorption of the intensity in far infrared, the conductivity measurements in this range is even greater than 10 minus 4 ohm meter. And so it's a very it's not very conducting. And then still oxygen has not reached its phase transition. But if there is a semi-metal, you should see something for reasonable conductivity smaller than 10 minus 4 ohm meter. You should see a decrease here. In the case of hydrogen, we saw nothing, no evidence of any decrease of this intensity, showing that there is some little druid edge here, showing that there is a number of carrier, and more so that we are here at 420 GPa with our scale. We should be 419 GPa with your scale, meaning that we are much above in pressure, and so it means that the increase of this electric density should have been much greater to claim. So I think there is no evidence of indirect gap from our measurements.
Thank you. We have a question from Francois, not know last name. Does the disappearance of the Raman or infrared vibron constitute indisputable proof of the transition to metallic hydrogen?
No. The disappearance of the in fact in in infrared, we saw the disappearance for the infrared vibron is due to the fact that the gap is completely closed, so there is no light going through the sample. So it's really the disappearance of this vibron is a consequence of the metallization. The fact that there is no transmission in infrared anymore. The gap is closed. So and for the Raman, you can measure the Raman until the visible gap is above your Raman signal, and we could measure the Raman measurements of D2 up to, I didn't show that, up to 320 GPa, but then the gap was closed and we could measure nothing. So the disappearance of the Raman of the vibron are no Raman vibron or infrared vibron are no evidence at all of metallization. It's a consequence of decrease of the gap.
Okay, thank you. I'd like to ask a question of my own. So there are many possible mechanisms for insulator to metal transition. Pure band structure effect, like was suggested by Marvin Cohen, or it could be a type of mode transition. So besides the very existence of the transition, what kind of experimental evidence can we have to attribute that to a given mechanism or another one?
I think the essential measurement now will be to measure the structure, to really be sure that it's the structure of this C2C structure up to phase. Then the calculations, it will validate the calculations or not. Then if not, we'll do other calculation, band structure. But then, as you see, in hydrogen, there's many complex electron phonon interactions and calculations. So it's so there's probably some reflectivity measurements can give information on interband transition. I don't know. This is something very complex. If you have a suggestion of
another completely different question. So with the toroidal cell, you reached 600 GPa, which is truly remarkable. Do you see any possibilities of doing even better? Do you have yourself plans or ideas of what to do to go beyond that?
I think most of our effort was put to make these hydrogen measurements. And for that, we were having we want to have a large sample. So we wanted to have a 6 micron diameter sample. Now, if you reduce your cullet tip and your torr, you can probably, if you make it to 10 microtorr, you can reduce it somehow to go to higher pressure. So the 600 micron, the 600 GPa on gold was obtained with 16 micron diameter torr. This one was for the flat. The flat was 16 micron. Here was 25 micron. So 25 micron hydrogen will reach almost 500 GPa. 16 or 18 micron will reach 600 GPa. So reducing a little, we can go into 700 GPa or so. And then it's already very, very good. If we can make detailed measurement up to this pressure, it will be fantastic. And probably the new beamline, the new high pressure beamline with the nanofocus submicron beam would be very helpful for that.
Thank you, Paul. Now back to Zoom. Question from Angelique Carosa. Do you expect a similar band gap closure behavior for hydrogen deuterium mixtures?
It will be, it's a mass, if it's a mass effect, it will be in between, but okay, it's not so interesting. And it can be very interesting if we want to disclose some quantum effect due to the spin of the system. That could be very interesting. If there are some magnetic properties of this metal hydrogen as have been predicted and calculated, this will be more difficult with very low temperature measurement, extreme pressure. Probably then we'll have to do some mixture, but it's not the first measurement now to progress and to be done.
Does anyone from the auditorium would like to ask a final question? Okay, so let's thank Paul again.
Thank you. It was a pleasure.